What? I am feeling a lack of enthusiasm from the back left corner. Empty. All right. Okay, here's where series start to get real. Before they were like, kind of made sense. And they're still going to maybe make sense, but here's where we start to get real. We are still going to look at the geometric series. So the basic geometric series is really easy because as long as you can figure out what the first term is and what the multiplier is, you can tell if the series converges or not because the multiplier has to be less than 1 or between -1 and 1, and you can tell what it converges to because we have a formula. So what's that formula again? A over 1 minus R. Okay, that formula is kind of like a general formula for a geometric series. We're going to look for a second at a geometric series. Oops. 1 over 1 minus x. It doesn't look like a series in the way it's written in that there's no series yet. Right now it's basically just a function that models what the end of the series is going to add up to. But what we're going to be asked to do is take functions now and write them as a series. Which might be like, what are you talking about? Like, what's the connection? But we can take lots of functions and write them as sums of stuff. So we can write them as series or series. Seri. So the geometric series 1 over 1 minus x, if we think about the fact that the sum is represented by a over 1 minus r, my a value would be what? 1. And my r value would be x. So this can be written as a series where the first term is 1. What's the second term? X. What's the third term?
X squared.
X squared. Okay, r is just the multiplier, so I'm going to multiply each term by x to get to the next one. The next one's going to be x to the third, the next one x to the fourth, and so on. These two things are equal. Kind of. This is a function. 1 over 1 minus x is a function. I can graph it. I can look at it as a function. This is a series. It's an addition of things all the way to infinity. This equals the sum when n equals 0 to infinity of x to the n. You can't put that series in your calculator in the y equals and look at a graph of it. But I can graph a bunch of terms of it. Okay, so we're going to take a focus a little bit on looking at functions, writing them as series. This is called a power series. Because it's made up of a polynomial. It's made up of a bunch of x's to powers, so it's called a power series. And we're going to take different types of geometric series and write them as geometric things that are geometric series, and we're going to write them as the series that they are. Now to back up for a second, what did we say has to be true about r for it to converge? R's got to be between 1 and -1, right? We said the absolute value of r has to be less than 1. So that means that r has to be between 1 and -1. Well, what this means is if I go graph this function and I graph this power series, they're going to be the same thing, they're going to look the same, only when r is between -1 and 1. So only when x, in this case, is between -1 and 1. That's why I have this handy dandy calculator thing up. Okay. Watch for a second. I can get this up here. And believe me, this is really supposed to be really hard to grasp in the beginning. I don't think I understood this until well after college. Yeah.
Yeah, that's good.
So, yeah, seriously.
So you're not even in college yet.
Depends, I guess, on your professor or whatever. But I really, until I started teaching this, I don't think I really understood it. Because I honestly think that a lot of professors don't understand it. So when they're teaching it to you in such a bizarre language that you don't really ever get it. So, what I'm saying is, if I graph 1 over 1 minus x, 1 divided by 1 minus x. No, you can just watch. I mean, as long as you can, like, stay awake. If you graph 1 over 1 minus x, so let me, like, zoom 6 this and take a look at it. It looks like that. In fact, I'm going to zoom, I'm sorry, I'm going to go -5 to 5.
EKG.
So, who really cares? It does not matter. You do not need it all to know what this looks like, although you would kind of know what it looks like. You should be able to kind of graph that on your own. This is just an asymptote. So it has these curves. I wish it didn't show the asymptote, but whatever.
Whatever.
Just because it's
So-
old.
Here's -1, here's 1. If I go graph this series over here, and I'll just graph a bunch of the terms. I'll go 1 plus x squared. I'll just graph that many. Let me make it bold. What I should look at is that the series and the function should match up from -1 to 1. And the more terms of the series that I give, the better the match should be. And they're only going to match up from -1 to 1 because we said the only time that the geometric series converges is when that r value, which for us right now is an x, is between -1 and 1. So we said a series only converges when r is between -1 and 1. So converges means the series matches up with the function that we're using to represent it. So this function and this series represent the same thing only between -1 and 1. So the more, let me make my window a little bit smaller. Let me see if I go like -1.5 to 1.5. The more x values I give in here, I'm sorry, the more like terms of the series I give, the closer the match should be. So let me go to my y equals. Let me make this just 1 plus x. And let me make this 1 plus x squared. And 1 plus x squared plus x squared. And let me make this one regular.
Add the trace, which is that circle thing.
The trace will like make it up. Yeah, I guess. That's a good idea to make the trace thingy. I'll make the last one, the grand finale, the thick one. Okay, ready? So it's going to graph the first one. It's slow, it's okay. So here's the second one. It's just the y equals 1 plus x is what I did. So like, it matches like from here to here, but it doesn't have that much of a space that it matches well. My next one that has an extra term on it matches a little bit better. And my next one that's bold matches a little bit better still.
That's awful.
And if I go, let's just give it a couple more. X to the, what am I at?
4, 5,
Goodness.
6, 7.
Where should
Where the first
Well, she just
No, that's just plus to the
Oh, I
7.
see.
Yeah, you don't have to count hope.
Shut up.
Oh, she still counted, right? She just got the S.
You can't count the variables.
Oh my gosh.
Now she just
So there's 7 terms of the series that matches really, really
match.
pretty well. Obviously, am I ever going to get an exact match?
Yes, if you go to infinity.
Yeah, but no, because realistically, I can't ever go to infinity. But if I could, I would, yeah. Don't be sorry, there's a million questions, yeah.
Be really sorry. Yeah.
That's not a question we want to ask right now.
No, that is the question.
The-
the wrong answer.
If there's no point,
There's got to be a point.
wait.
No!
What's the question
You
going to
don't
be
even
like?
know the point?
This doesn't seem that.
You don't need
It is kind of cool.
What's the
This is
question?
invalid.
Wait.
Hey.
So essentially,
This is what
this is what we're
the world.
working towards, knowing how to find what we're looking towards
This
is,
is
if we're given a function, what series can we use to represent that function?
just from negative
That
1
will
to 1.
match it from -1 to
That's
1.
the
But
stupidest thing
we
ever.
will continue and we'll get series that will match for all real numbers. But this geometric series only match from -1 to 1.
And why is this important?
Because that's all they do.
So how's the question? What's
How
the
much
question?
literally can
What is the question going to be like on a
I'll
test?
show you. What?
The only time we're ever going to need this in our lives
Is in calculus
the
class.
DC test.
Yes. All I can tell you is if you're going to take Calc 2 in college, be happy you're getting it here from someone who I think understands this, and not from, and you can understand
Are you
me,
saying
and
you're
we can
better than
be in a
others?
safe atmosphere. What's that?
Are you saying you're better than others?
No, but I did not understand it from my college professors. I didn't, and maybe because they explained it, what?
I said something that can't get
In a way that was out there, and maybe I'm dumb enough to be able to explain it to the masses. I don't know. But I just know that this was really a crazy concept when I got into college. So, yeah.
What other series
Let you in.
that aren't geometric series?
Some series that aren't geometric will match for all real numbers.
Are we gonna get there?
Yes.
Are we gonna be terrible?
Yes.
Can
No,
I
we all
speak now?
Why are you so happy?
because it's just such a hard concept. It's so great. I love
Wait,
it.
how much harder does it get than this? Like
A
right
lot
here?
harder.
Okay.
Yeah.
Because
Alright,
that
question,
seems
what's the question
simple.
now? Show me
Okay.
the question.
Okay. Gosh, just slow down. So, like,
Jeez.
I gotta go slowly so number one, you don't get confused, and I don't get confused. Okay? So. It's
At least you
I find it difficult to explain because I think it's complicated. Shut up.
It's like,
My earring stuck
yeah,
to
I
my
didn't
sweater.
understand the problem either.
And
it's on camera.
I hate that.
That's
What would
saying
Monica
those are
do?
my Twitter. Or those are-
WWMD.
Okay.
Oh, yeah, maybe.
All right. Okay. So we start asking a question. Given a function, write a series that represents the function. Okay. So I'll try to write up a lot of what I say so that you can have in your notebook. Given a function. We're going to write a series that represents the function.
Only between -1 to 1.
Well, yes. I'm sorry, I didn't make this stuff up, okay?
You did.
So right now this is what we call our basic geometric series, 1 over 1 minus x. And most other series come from that. So we kind of use it as a model to represent the series that come next. So we can look at this a couple different ways. The first way we can look at it is figure out what our A is and figure out what our R is and start writing it. So because it looks like a geometric series, and when I say looks like, I got a fraction, and on the top I've got a constant, and then I've got 1 minus some x term. So like that general form lets you know this is most likely geometric. We can confirm it by, well, it's geometric because of the way that it's written. So we can take it and we can write the first few terms out. So we know that A is 3, and R is x to the third. So if we want to write a series that represents this function, I can just start. My first term is 3. My second term is 3x to the third. My third term is 3x to the sixth, 3x to the ninth, blah, blah, blah. So I won't get this thing out because you get it now, but if I were to graph this, and I were to graph a bunch of the original, or these first few terms, they will be the same thing, from -1 to 1. But I also have to be able to write a general term for this. So here's where it gets tricky. General term meaning in like the sigma notation. Okay, so the general term for this, and it's going to go from something to infinity, and we can choose if we want it to go from 1 to infinity or 0 to infinity, depending on how we want to write this series. So does everybody agree there's a 3 in every term, so I'm going to go 3. and then I'm going to go x
The 3n.
to the 3n. And then n should go from what to infinity?
Zero.
0. Okay, because of the first term, I can't have any x's in it. I want n to start at 0, and then I'll be good. I always check myself after I write a series. I'll check like the first two. Definitely the first one, just to be sure that it works, and so it does. Okay. I can write a series in one of two ways. This is the first way I can write it, by getting my a and my x and writing it all out. The second way I can write it is I can take the series I already know and substitute. So since I know that 1 over 1 minus x is the series when n equals 0 to infinity of x to the n, it's a little bit trickier than 3, but then 3 over 1 minus x to the third, I can basically just substitute in, instead of x, I'm going to have x to the third. And then this 3 is kind of just a multiplier. It's a number on top. It's just a multiplier. I could almost take it out. This is like 3 times 1 over 1 minus x to the third. So it's just 3 times that.
Seems like only it's good.
It's just going to depend on the problem, which way is easier. So sometimes it's a lot easier to substitute. You can't only know one way. You're going to have to know both ways, because sometimes the only thing you can do is substitute. So we'll look at a couple more right now. But again, to write a series, we can either say, here's A, here's R, give the first few terms, and then from there, write our series. Or be like, well, I know what this series looks like, so here's one that's really similar. Instead of x, I'm going to have x to the third, and it's multiplied by 3. So I can just rewrite it that way too.
Is there a case where it wouldn't just be a times r to the n?
The only time I can think, like, when you start getting the changing of sign, plus minus, it gets a little weird. But let's look at, I don't know, there's nothing coming in my head that I can think of to give as an example. So we'll just have to see if something comes up that we can. Okay, so here's another example. Alright, let's do 1 over 1 plus x. Sorry.
Here's my error with it.
I think I like pulled my ear hole.
Sounds impersonal.
Okay. Alright, 1 over 1 plus x. We should know it's geometric. What's the first term? What's the a?
1.
1. What's the r? Negative x. Good. Okay, the geometric one we know, like that we start with, is 1 over 1 minus x. We just have to be careful with the sign. What we know is 1 over 1 minus x. This is x to the n. To start at 0. So you can again list out the terms. So the first term is 1, and the second term is negative x. And then we've got positive x squared and minus x to the third and positive x to the fourth. So this is what I was talking about the other day, when the sign switches back and forth from plus to minus. We have what we call an alternator. The series is called alternating because it goes from plus minus plus minus. So I just like to think of this as I'm going to have a negative 1 to the n, and I'm going to have x to the n. I understand that this is the same thing as negative x to the n. I think it's easier to, whenever my signs alternate, to have that negative 1 in front, because then I can make sure I pick my n values correctly. Meaning, I want n to go from what to infinity? I have to go from 0, right? Because I need x to the 0 to be 1. I need my first term to be 1. Does that work for the sign? Is negative 1 to the 0 still just positive?
Yes.
Yeah. So I'm good. It's possible that when I do this, the the sign ends up not matching. Like my first term was really supposed to be negative, but I needed x to be 0, I needed the power to be 0 first, so that my x was just 1, and I got rid of my x completely. If that ever happens, I can always make this like +1. If I need my signs to alternate differently, I can always make the power of the -1 like n+1, and that way, like my first,
Darren, we're here.
They wouldn't let us leave.
let you leave what?
We have nothing with it. We were from Deca.
How'd that go?
Amazing. Mac did a good actually.
Yeah? Are you guys finished?
Yeah, he won his test.
No way, nice job.
First place.
Best in the state.
Look at you.
My partner is very sick.
Who's your partner?
KJ goes to sleep.
That sucks. Alright, anyway. That's right, that's the end.
But you can put negative x to the end?
So this one, we could have just substituted just like before. So if we wanted to substitute it, we know what this one looks like. So we could have just gone -x to the n, n equals 0 to infinity, and be done with that. So I just wanted, like, I always just double check the signs and make sure. Let's look at another one. Alright, you'll love this one. No, I'm being a little bit sarcastic. Okay. So again, this one's just like geometric. In fact, it's almost easier than the one before because the signs all match up. It's still minus, like this was minus. I'm not going to alternate. It's going to be just fine. So go ahead and try to write the series for this. So, I don't want to rush you. Sorry. So I get the first, I did it the first way by just writing out the first bunch of terms. A is the 1, R is 2x. So I got 1, 2x, 4x squared, 8x to the third, blah, blah, blah. Depending on how I'm thinking about it, I can look at this as I've got 2 to a power and I've got x to a power. And they're both to the same power, so this works just fine. I also could have thought about substituting. If I substitute in for the regular geometric series that you know from the beginning, then, pardon me, I would just put 2x in and it would be to the n. And that would be fine also. Is that okay? Here's the difference between this and any of the other ones. We always said that it converges from -1 to 1, right? Well, that was because r just equaled x. And since r has to be between -1 and 1, x has to be between -1 and 1, or the absolute value of it. But now my r is something different. So r has to be between -1 and 1. So in this case, 2x has to be between -1 and 1. So therefore, x itself is between 1/2 and -1/2. This one only converges when x is between -1/2 and 1/2. So this is called the interval of convergence. A geometric series converges when r is between -1 and 1. But if r is anything complicated, if r is not just an x, it's like a 2x or a 5x or whatever, my interval of convergence changes. So this is the first time I've used this word. It's called an interval of convergence. We haven't worded it like that. We've just said it converges on this interval, but it's the same thing. Fancy word is, and you could be asked, write a series and give the interval of convergence. So I don't want to take the time, but if I went and I graphed this, and I graphed a bunch of these, it's only going to match from when x is -1/2 to 1/2 now. instead of negative 1 to 1. So the interval convergence is just smaller. Is that okay?
When we get into the calculus,
We are.
this
This is considered still calculus.
really.
Yeah. Let's just do one more, and we'll leave it at that.
This is calculus?
No, it's not. This is dumb algebra.
Wait, yeah, when does
Seriously.
calculus end?
It doesn't really, although when we get tomorrow, you can
Not
write a
gonna be
series by
tomorrow.
taking the derivative of an original series, and take the derivative of all the terms, and get a new series out of it.
And then you have to punch it.
You'll see. It's pretty cool, actually. Alright, one more.
Advanced derivative series.
Ask Matt. No, I actually.
That was weird.
Alright, some big series, I hate that word plurally, should stick out in your head. So the geometric series is going to be one, like, you might as well start to try to memorize it now, because you're going to need to always just be able to kind of recall it quickly. This is also one that's good. So what did we just say? How does this one get written when it's plus?
Negative 1 to the n.
Negative x to the n. So, if we're going to take a new series, or we're going to try to write a new series, I don't have to always go back to this one. I could go back to this one if I want to. Okay? I don't have to go back to the original geometric one. I can go back to any other one I've written ever. So, even if I had, if I knew what this looks like, and now I had this, I could take this one out and like multiply them all my x's by 2 or something. Like I can manipulate old series that I have. Yeah, I don't want to make it too confusing, but this one I don't have to go back to the beginning. I could go back to this to try to kind of rewrite it. So what makes this one so weird is my a is a variable, and this is the first time that's happened. So this time a equals x and r also equals x.
Is that still
R equals negative
geometric?
x. Negative.
Oh, that's sorry.
Oh, yeah, it is.
Yeah. Okay, so if I'm going to write the first few terms, I'm going to have the first term's a, the second term's negative x squared, the next one's positive x to the third, minus x to the fourth, plus x to the fifth. If I'm going to write this series, I first of all see that it's alternating. So I'm going to have a negative 1 to the n. And I'm also going to have an x to the n. But I'm not finished yet.
Uh-oh.
Here's where I have to be a little careful of the signs and the powers all matching up the way they should. If I leave it like this, first of all, if I just look at x first, what do I need n to start at?
1.
1, right? I need or n to start at 1. So that I have an x to the first, because x to the first is where this is starting. But if n is 1, this is wrong. Because negative 1 to the first is negative 1, but my first term's not negative. So I just need to switch this. I need to just put this in as n plus 1. Or n minus 1. Either way would work. But now, it's starting me off at n plus 1, which is 2, to negative 1 squared gives me that positive starting spot. And then my x term is also correct. So you just have to stop, look at your first term, and maybe change the powers. It's mostly going to happen, or it's really only going to happen when you have that alternating series. I could also have rewritten this in a different way. If I wanted to start at 0, because I was really excited about my negative 1 being to the n,
N plus 1.
so then n is 0, so my first term is positive, well then this one needs to be n plus 1. So either one's fine, they're both correct, they're just different.
Super.
Is that okay?
Yeah.
Is there like a little bit of fullness?
You done?
A little bit. We're finished. Alright, try these 3 problems tonight.
Nope.
People who save the homework, Corey, I would maybe, Corey, just do these, Corey, as I go. Corey,
I don't do the homework either.
and then you might feel better about it.